So let us recall, in the last class we have discussed Taylor's theorem or formula with Lagrange's and Cauchy's form of remainders. Then we have seen Maclaurin's theorem Okay. Third, we have seen some applications where of Taylor's and Maclaurin's theorem. And we have seen that if we tend n, that is the nth term, if n tends to infinity, we will get Taylor series. A theorem, this theorem will give us the Taylor formula or the Maclaurin's formula. Will give us Taylor's series. Okay, Taylor's theorem will give us Taylor series and Maclaurin's theorem will give us Maclaurin's series. Okay, and then we have mentioned that Taylor's theorem and Maclaurin's theorem, they are actually used to approximate for approximation. Given a function, we can approximate it by Taylor's polynomial. Okay, depending on the function, we will choose the polynomial. Okay. Now, and then we have simply briefly we have defined the idea of asymptotes. So asymptote is basically a line which is asymptote is a line asymptote to a curve. Okay, asymptote is not a separate thing. It must be to some curve. Without it, it is not an explicit thing. So if a line which lies in the finite distance from the origin, then if we have this type of relation that as x tends to or y tends to infinity, here y tends to infinity and x tends to infinity, then the distance between this line, this vertical line or horizontal line, okay, this tends to this distance is tending to 0 as we move forward along this curve and this line, the distance will gradually go to 0. So that is the geometrical meaning of a asymptote. Now there are three types of asymptotes: vertical asymptote, horizontal asymptote, and oblique or inclined asymptote. Okay, in the last lecture we have seen that if we have curve like this, if the given curve is this form, then an oblique or inclined will be like it will make some angle with the x-axis. So this is oblique. It could be like this one. So how to find vertical asymptotes? For vertical asymptotes, as you can see that for vertical asymptotes, if we want to get a vertical line, then x must be some constant. If we put, then we will get a vertical line. So in that case, in other words, if we can write the given function, if the given function is this one, if you can write y equals to f of x, which is a in terms of x, suppose y equals to x minus 1 by 2x plus 3, this type of functions. Okay, if we can separate them, or you can write it y equals to 1 by x minus whole cube, or 1 by x minus 1 whole square. So this type of functions, if we can write y as a function of x, then we can easily find the vertical asymptote for this type of functions. I mean those type of curves. Okay. So how do we do that? We'll try to find this limit, whether it is satisfying or not. If it satisfies, then x equals to a, then here x tending to a, so this line will be a vertical asymptote if this property holds. Okay. So similarly, for vertical asymptote, you can see that for x equals to a, this is x equals to a, this line is x equals to a, and this is a given function, a given curve. Then what we know that as x tends to x is tending to a, okay, this y limit, okay, you can see that this y becomes infinity, okay, plus infinity. Then we can say that this is x equals to a is a vertical asymptote. For here, okay, x goes to 1 plus, then it will go to the plus infinity. Okay, this. So if you take this limit, y plus infinity. If you take the left hand side limit x goes to 1 minus. Then if you take this y, it will be minus infinity. So by property, by the definition, if we have x goes to a, this is y equals to, if it is plus or minus infinity, then we will call x equals to a is a vertical asymptote. So here for this particular curve, okay, for this particular function, this function is actually f of x, y equals to f of x 1 by x minus 1 cube. So if you draw the curve, so you will get this two separate halves of this curve. So this is more or less the vertical asymptote. Okay. Now, if we take another function for vertical asymptote, okay, so both of them, okay, this curve, okay, this is a C1 and C2, curve 1. Actually, these two are actually given by these functions, those two halves. Now, x tends to a, whether we go for this positive direction or negative direction, okay, then limit of y will be plus infinity, and x goes to, if we go for left hand side limit, then also it will go to positive. Okay. So that is for vertical asymptote. Okay. Therefore, the curve approaches to. Okay. For this type of functions, the curve approaches the same end as the asymptote one. I mean, whether it will approaches to the line in the same direction or not, it will depend on the multiplicity. It will depend on the multiplicity of the problem. Since it is a odd number, okay, odd number, so we will get two different directions, plus infinity and minus infinity for odd numbers. And this is 2 is even number. For even numbers, we'll get this in the same direction. Okay, either it is either this is plus infinity and minus infinity. So this is over minus infinity. So any direction it could be. Okay. Now, how to find the horizontal asymptote? Okay, for horizontal asymptote, for horizontal line, we need to get y equals to some constant. So then we will get horizontal lines. Y equals to some constants. Okay. So here, suppose we consider this y equals to 0 for the same function. Okay. This is y. Now the definition is, if we can write this function as a the given function as a function of this form. That means, so here it can be written as this function. So if you take it, so from here you can write it x minus 1 equals to 1 by, similarly x can be written as 1 plus, so finally we have x equals to 1 by 3 plus 1, right? So this is actually h of y. So we can write it as a function of y. So now we have to take, now x goes to 0 when, suppose q of y goes to, sorry, x goes to infinity, plus or minus infinity, if q of y goes to 0. That means we have to note that if we take this limit y tend to b, h of y goes to plus minus infinity, then y equals to b is a horizontal asymptote. Horizontal asymptote. Then the line is called horizontal asymptote. And note that if we have this form, so q goes to b, and this x goes to infinity is actually plus or minus infinity, is actually meaning that q of y, okay, it is 0. That means y equals to b is a root of the given qy equals to 0. Y equals to b is a root. Okay. So we'll write it as a, and we'll see that. So for this horizontal, this asymptote, we can also define in that way also. We can use this formula also. If we get any finite number b, such that okay, the function, the given function we have written y equals to fx by qx. So we will tend that to infinity. Earlier we have seen that we have, if we do this, if it is plus minus infinity, then it will give us vertical asymptote. But now if we allow this x plus minus infinity, and if the limit is a finite number, then this will give us horizontal asymptote. Okay, so we will see with some examples.
Sir.
Yes,
Yes, sir. So there was a concept that the asymptotes and curve differs only in the constant term. So there was a concept in 12th class. We have studied that the equation of asymptote and equation of curve differs only in the constant term. Like their equation is same, but only the difference is of constant term.
Okay.
Sir, but here, like in the equation y is equal to 1 upon x minus 1 whole cube, the asymptote is x is equal to 1. But sir, the difference is not only in constant term. Whole the equation is changed completely, sir.
Actually, I don't know what you have studied earlier.
Sir, we have studied that the difference in asymptote and the equation is only a constant.
No. That is since it is since this was 12th class knowledge. Okay, but now you have one class higher. So here we will define more mathematically. But geometrically, asymptote means it will. What you are saying actually, the difference between
Equation of asymptote and equation of curve is a constant term only. Like sir, in hyperbola we have studied this.
Okay, so for hyper, okay, there is only difference is constant term. So here, so suppose x equals to 1 and the function is y equals to 1 by x minus whole cube. Okay, the difference, if you take this difference, so this is not a constant term actually. Okay. See, the difference is the definition. Okay. The definition says the distance between this line, okay, this line will be called asymptote if the distance, that is not the difference actually, the distance gradually decreases. Okay, that means if you extend this y, okay, it will go close and close, very close, but it will not, okay, match. It will not overlap with the curve.
Sir, suppose I am giving an example. Like the equation is x square upon a square minus y square upon b square is equal to 1. Minus, there will be minus, sir. That hyperbola equation.
Okay.
Then the equation of asymptote of this curve are x square upon a square minus y square upon b square is equal to 0. Minus
X
y
square
square
upon A square by
minus
minus.
y square upon b square is equal to 0. These two are the asymptote of this hyperbola. They differ only in constant term like 1 and 0. Earlier this concept was told to us in class 12.
This is you are telling about this is a asymptote.
Yes, sir.
Sir, pair of equations of asymptotes, sir.
Uh-huh.
That
Can
is
you
the
repeat?
pair of equations of asymptotes, sir.
Pair of equations. No.
Combined form of equation, sir. As we will write x square upon a square is equals to y square upon b square, we will get x upon y is equals to plus minus a by b.
Yes, sir, it is combined equation of asymptote. But here also, sir, in the equation, if we see combined equation, we are getting incorrect, sir. Like y is equal to 1 upon x minus 1 whole cube, x is equal to 1 is asymptote.
Sir, it is only applicable for hyperbola, I think.
Yes, sir, it is one applicable hyperbola.
Because hyperbola has a different shape, right?
Yes, sir, it is clearly mentioned that it is only applicable for hyperbola also, sir.
Okay, so hyperbolas are like this one. This is okay. Anyway, I would recommend you to revise, to recall the knowledge again, to compare again. But
Sir, one
that
more
is
doubt. It is clear,
that
sir.
is not a correct approach.
Yes.
As per this BTech level, that is not a correct approach. That the difference is constant. The difference will become tending to 0. See the definition. Okay.
Okay, sir, clear.
Okay.
Sir, one more doubt is there. Like, sir, in some cases, if you will not be able to like make the difference, like y as a function of x and x as a function of y.
Yes,
in that,
yes. That all the things we will discuss.
okay, sir.
Just hold on. Hold on.
Okay, sir.
Okay. So, okay, where were we? Okay, horizontal asymptotes. Okay. So horizontal asymptote and vertical asymptote done. Now the third type of asymptote, that is inclined or oblique asymptote. Okay. For vertical or horizontal, we will have y equals to some constant or x equals to some constant. Okay. So this will give us horizontal or vertical line. But for inclined line, we have to we will have this type of lines or this type of lines. It will be like this way. So for inclined lines, the equation of the asymptote, that is the asymptote line, will be ax plus by. Ax plus b. That's it. So the derivation is actually, if you are interested, you can go through it. But I'll just tell how to find the final formulas. Okay, we will define, note that ax plus b is our target. Okay, this is our we have to find it. We have to find it. So we will define y equals to fx given. We will write the function as this form, or this is p by q, px by qx given. Then we will define a. We will define a as this limit x goes to infinity plus minus, actually plus minus x goes to infinity, here also plus minus x goes to infinity, and b, after finding a, with the help of a, we will define the b as the x plus minus goes to infinity fx minus a into x. So these two, once we get these two limits, okay, if we get these two limits, a and b, then we can directly substitute those values here. So we'll get the inclined asymptote. Now note that if any one of them does not exist, any one of them do not exist, one or both do not exist, then which means it will mean that the inclined, there is no inclined asymptote. Now if a equals to 0, okay, after finding this the limit a equals to 0, if a is 0, then from this equation we can see that b is a y equals to b. So that is, we will get a horizontal asymptote. Okay, so these two are, we will see them with an example. Okay, so another approach for inclined. Okay, for inclined asymptote, there is another approach. We can we will define this function as y equals to fx by px by qx, and after this we will separate them. We will write one y equals to, this will be our x plus b. Okay, on one inclined line we have to pull out of this function, so that not every time we will be able to write this type of functions, but we have to pull it if it is possible from the given function. Then we can write it as one straight line plus one ratio will be there, that is Rx plus Qx. The degree of Rx is less than degree of Qx. Okay, so that if we allow x tends to plus minus infinity, that this term will go to 0. Okay, because we will have degree of the degree of Rx is less than the degree of Q. So it will be like this form, x by x square, either this type or this type, or x or this type. So this type of functions will be there. This ratio we have to write in this form. So if we allow x tends to plus minus infinity, then this term become, okay, this will go to 0. So that the y equals to ax plus b will be our desired asymptote, inclined asymptote. Okay, this is one approach. Either we find the limit, or you can go for this approach also. Okay, so for example, if we take this function, okay, if we take this function, then we can see that x equals to 0 is a x equals to 0 or y-axis. It's a particle asymptote. Since x tends to 0 positive, remember that x limit x goes to a fx, or this is if it is plus minus infinity, then x equals to a is a particle asymptote. So here we can see that if we allow x goes to 0, then this function, okay, y is actually tending to plus minus infinity. So here a is 0 or So x equals to 0 is that means the y-axis. The y-axis is the vertical asymptote. Now this function, okay, can be written as this form. Like this is Rx, degree of Rx is 5, 0 degree polynomial, and degree of Qx is 1. So as we will allow x tends to infinity, then this whole term will go to 0. So y equals to 3x square, 3x plus 1 by 2. This part will become inclined asymptote to the curve. Okay. Now for a different problem, we will get this type of functions. Suppose fx is this one. Okay. The question is find the asymptotes of the given function. So if you just look at this function, if the first part of this function, then we'll get for x greater than 1, we have this one 2 plus, okay, this is just we are just separating 2x so here this is y equals to 2 and x equals to 1 will be the horizontal and vertical asymptotes, and this line is actually 3x, y equals to 3x plus 4 is an inclined. Okay, you just need to verify. Everything is written here, so you can verify it. Okay, now we'll see 2 more examples. So let us take the second example. So here the given function 2x plus 3 into y equals to x minus 1 whole square. What we'll do? We'll write y equals to x minus 1 whole square 2x plus 3. Okay. So from here we can write okay. Now if we take limit x goes to 3 by 2 minus 3 by 2, right hand side limit and y, then we'll get this will become plus infinity. Okay, and limit x goes to minus 3 by 2 minus, this will become minus infinity.
Sir, I think it's opposite, sir. In first case, it will be minus infinity. Second case, it will be plus infinity.
No, it is correct. That's correct. So, by definition of vertical asymptote, x equals to minus 3 by 2 is a vertical asymptote. Similarly, if you write how about that? What was that? In order to get horizontal axis, we have to write x equals to h of y. Okay, that was one approach. Another approach was if limit x goes to plus minus infinity, and that was f of x, given f of x. If it is a finite number, okay, then if we can find a b such a finite number, then y equals to b will be the horizontal asymptote. So for here, if we take here, so limit x goes to plus minus infinity. Okay, or you can just the function is x minus 1 square by 2x 3 by 2. Okay, so what we get? So if you just write limit x goes to x square minus 2x plus 1 by into x by 3 by 2. So from here you will get, so if you divide by x, it will get x minus 2 plus 1 by x. So 2 into 1 by 3 by 2x. Okay, so as x tends to infinity, so this term, these two terms will go to 0. Okay, these two terms will go to 0. Okay, but x is already there, so it will become infinity. So this becomes infinity. Okay, this is not a finite number. Okay, not finite. Not finite. So we are not able to satisfy this this equation. So there is no horizontal. There are no horizontal asymptote. Okay. Now, how about inclined asymptote? So y equal to x square minus 2x plus 1 by 2x plus 3. So it can be written as 1 by 2 x minus 7 by 2 plus 25 by 4 divided by x plus 3 by 2. Okay, now as x tends to infinity, plus minus infinity, this term 25 by 4 x plus 3 by 2 goes to 0. So y equals to half of x minus 7 by 2 is a inclined asymptote. Now there are the limiting definition. If you think about the limiting definition, so let us go. We define A. Okay. It is not every time possible to identify this fraction. Okay, so it is better to go with the limiting value. So the A is the limit over x goes to plus minus infinity, and fx by x by definition is this one. So what we will get here, the limit x goes to infinity. Let us take first plus infinity. Okay, plus infinity. Then it will be x square minus 2x plus 1 per side numerical. The numerator and the denominator is x into 2x plus 3. Okay. So you will take just, you can write it as 2x square plus 3x by if you divide by x square. Okay. Then you will get x goes to infinity 1 plus 1 minus 2 by x plus 1 by x square 2 plus 3 by x. Okay. So as x tends to infinity, this limit will become up. Okay, this will go to 0, this will go to 0, this will go to 0, and the it will only remaining thing is 1 by 2. So half. So in order to find this b, we have to define limit x tends to infinity. What is that? Fx minus a times x. So a is our half here. So we'll write it half. And fx is given as this one. So we'll write it as it is. Fx is x square minus 2x plus 1 by 2x plus 3. Okay. So now if we simplify b, limit x tends to infinity, what we have? We have x square minus 2x plus 1 by 2x plus 3 minus half into x. Okay. Two x square minus 4x plus 2 minus 2x square minus 3x divided by 2 times 2x plus 3. So this 2x gets cancelled. We will have limit x goes to infinity minus 7x plus 2 by 2 times x plus 3. Okay. So if you just take the limit, okay, if you divide by x, again x, so you'll get minus 7 by x, 7x by x, etc. So this is okay, it's plus 2 by x, then 2 by this is 4, 2 into 4 plus 6 by x. So as x tends to 0, sorry, x tends to infinity, we will have the limit is minus 7 by 4. So y equals to a plus ax plus b is the inclined asymptote. Okay, so we will have y equals to half x minus 7 by 4. Okay, so we can take it 1 by 2. Now this is actually same as what we have written as a function, alternative method. This one. So not every time we can write the function, okay, in this form. Then it is better to go with the limiting approach. Okay, so this is our the required inclined approach, asymptote. Okay. Similarly, you can do this. Okay, the first example, given this curve, okay, you have to find out the horizontal, vertical, inclined and horizontal. There will be no horizontal asymptote. So you just have to verify them. Okay. Now asymptote for a parametric curve. If it is not given, for example, x is parametric is this polar form is also a parametric form. So if it is x equals to x of t, suppose 3at or maybe 3kt, because a we have already written at by 1 plus t cube and y of t is equals to 3a square t square by 1 plus t cube. So this type of functions, if we have, then how to get the asymptote for this type of functions? Okay. For this type of functions, we have to first we have to identify whether any one of them becomes infinite or not at some particular point, t equals to t0. At some particular point, t0 point, whether it is becoming 0 or not, any of them. So if any one of them becomes 0 and others remain constant, others remain finite, not constant, finite, then we can find the asymptote for parametric curves. So if this one is plus minus infinity, phi of t0, and the other function psi of t0 is constant, then the curve y equals to c is a horizontal asymptote. Similarly, if we have the first curve as a constant at some point t equals to 0, t0 point, and the other function becomes infinite, then we will have vertical asymptote. Okay. Similarly, for inclined, if both of them are infinite, then we can find, we may try to find an inclined asymptote. And by defining the limits, okay, the limits we have seen already, that earlier we have seen that fx by x, a was the limit of, okay, so here it will be the ratio of the two functions. A will be the ratio of two functions, and b can be written as the similar way. Okay. So if we have r equals to f of theta in the polar form, then we'll substitute x equals to r cos theta, and r is a function of theta. Similarly, so the function becomes phi of theta, and y equals to r sin theta. So this becomes psi of theta. So this will exactly be of this form. This one and this one will be. Now we can proceed the above approach. Okay. So for example, here A, remember A is a constant here. Okay. Not that our A. That is why we are writing here. Suppose there is a inclined. There are no horizontal or vertical asymptote because both of them are finite. As so, if you just take this, both of them tends to 0. Okay, if you divide by p or t square by tq, then if you divide by t, the left hand side, okay, this, okay, t tends to infinity, it becomes 0. Here it is also becoming 0, tending to 0. A is a constant. So we'll write the function as inclined. Okay, for t equals to, if t goes to -1, then both of them becomes infinite. So for inclined asymptote, we have to write this form, where m is the, by definition, m is this one. So phi of x of t by x of t by, sorry, y of t. Okay. Let me check. Psi of t. So the second function, y of t by x of t. So this one will give us the -1. Okay. Now once we get this m value, then we will define the b value. B will be this function. So here we are getting this, and here is a constant. So the function, okay, the inclined asymptote is this one. Now this parametric equation, if we write the Cartesian equation, this will become in this form. Graphically, it will be like this. So this line is a asymptote to this curve. Now the question remains, if we cannot separate them, okay, if we cannot write them as a function of x, or x cannot be written as a function of y, then how to find the asymptotes? Okay. Since this is the algebraic equation in polynomial in xy, and all these type of functions are okay. For this type of functions, we have to consider the following approaches. Okay, for horizontal asymptote, we have to suppose this is a function in this form. Okay. So x to the power n into g of y. So here x to the power 0 into, this is g of g of y. Similarly, this is x. Okay. So if the function is given in this form, then we will divide this equation by x to the power n. Once we divide it, x to the power n, x to the power n, x to the power n. So we'll get this next equation here. Now, as x tends to infinity, okay, both of them, all this term will become, and this goes to 0. Only term remaining g0 of y. Okay, g0 of y. So if this g0 of y, we'll get this. If g0 of y is a constant, or it does not have any real root, because this function, okay, if we solve g0 of y, it will give you an equation in y. If there is no real value of y, suppose we get some a plus bi, some complex number, okay, y equals to some complex number, then there is no horizontal asymptote. But if the real roots are, if this equation has real roots, okay, y equals to c1, c2, cn, then y equals to c1, y equals to c2, and y equals to cr will be the horizontal asymptote to the given curve. That means we have to take, so what we are doing actually, we are considering the highest degree term in x. Okay, whatever the mechanism we do, we are only bother about this term, the highest degree of x, and we'll equate the coefficient which is a function of y, okay, equal to 0, we will equate to 0, and we'll try to find the asymptote. Okay. For example, if you take here one example, suppose x square plus y square minus x square y minus xy square plus x plus y plus 1 equals to 0. Okay, so we cannot separate this one. This cannot be written as f of x or x equals to f of y. Okay, it is very difficult to find out. So we'll rewrite this equation. Okay, rewrite. We take the x square y square minus y plus, okay, leave it as it is. Then we will equate this 0. Okay, if we equate this 0, equate to 0, then it will be y into y minus 1 equals to 0. So we get y equals to 0 and y equals to 1. Y equals to 0 and y equals to 1 are the horizontal. Asymptotes. Okay, horizontal asymptotes. Similarly, if we have, if we can think of this function as a y to the power n and a function of x, we'll do the same thing. We'll equate the highest degree, the coefficient of the highest degree in y Okay, for the same example, if we take y square, x square y as x y square, x plus y plus 1 equals to 0. So we will take y square, x square, this minus x, okay, y plus x. Okay, so we'll equate this on 0. So x into x minus 1 equals to 0 will give us x equals to 0, x equals to 1 are the particle asymptotes.
Sir, x equal to 0 is a asymptote.
Yes, of course, x equals to 0, that means
Sir,
y-axis.
sir, y equal to minus 1 is satisfying on that point. X comma 0 comma minus 1.
Y equals to 0 comma minus 1.
Yes.
Okay, you're talking about x for suppose x equals to 0. No, it will not satisfy. I am telling you what I am telling you. They will approach to 0. This is a given curve. This is a given curve. Okay. So if you put here x equals to 0, then we will get 1 equals to 0. So it is not like that. We do not. It will not satisfy. This.
Sir, we have y now. Y equal to
That,
minus 1.
which one?
Sir, we put x equal to 0, then y equal to minus 1 satisfying now, sir.
No. I told you that the asymptote and the curve will not overlap. If they overlap, then they will satisfy, right? This suppose this is x equals to 0, that y values. Okay, the distance will approach to 0. If we go to infinity, then the distance will go to 0. So if you put x equals to 0 here in the given equation, so it is not like that. It will not satisfy, because these two, this asymptote is also a straight line. It is, you can call it, it is also a curve. Line is also a curve. Okay. So it will not satisfy this. If you do that, am I audible to you?
Yes, sir.
Now
Yes,
you're
sir.
audible.
Okay, actually there is a power cut, so I am connecting through mobile now. So anyway, the thing is that they will not satisfy. Okay, the points of the asymptote, all the points of the asymptote will not satisfy points of this asymptote. It will not satisfy the given equation because they do not overlap. They will not intersect. They will go as long as. Okay. They can come close. The distance will go to 0, tending to 0 at the infinity, as x tends to infinity or y tends to infinity. But they will not. Okay, this asymptote will not satisfy the given curve. That is the idea of asymptotes. Okay, so for inclined asymptote, okay, for such type of functions, I would recommend you, this is taken from B.S. Girwal. Okay. The formulas are, okay, the mechanism I will explain. These derivations are, if you are interested, you can go through it, but I will explain the mechanism only, the working rule. Okay. So what we have to do, we have to find some functions phi of order n, phi n of m, a polynomial in m, because y equals to mx plus c is our target, inclined. So we will put x equals to 1 and y equals to m in the highest degree terms. Thus, we will get m polynomial, okay, n degree polynomial in m, a polynomial in m. And we will equate to 0 and solve for m. Let the roots be m1, m2, and mn. We will find out. Similarly, we find out a polynomial phi of n minus 1 into n1 of m by putting x equals to 1 and m. So for n degree, we'll take the first we will consider the xn, then we will consider x minus 1, x to the power n minus 1 degree, and we'll do that again. So find the values of CE, where C1, C2, and Cn by substituting m equals to m1, m2, and so on. We'll define the C as the minus phi minus 1 of x, sorry, m by phi of m. We'll differentiate this one. Okay, sometimes we may get 0 form to find out. We have to find out from, then we have to find out this C from this equation, this recurrence equation. Then we substitute, after finding the m and C, we'll substitute these values to get the inclined asymptote. So let us see some example. Okay, so for the first example, we have to find, so the degree is 3. Okay, for x to the power 3 or x cube, we'll define this phi 3, phi 3 of m. Remember, phi n of m. So the 3 degree terms are here. This one is 3 degree. This one is also 3 degree. This one is also 3 degree. Again, this one is also 3 degree. Okay. So for this type of equation, we will put x equals to 1 and y equals to m. So if we put x equals to y equals to m here, m cube, then 1 into m square, and 1 square into m, and 2 into 1 cube. That means we will get this equation. Okay. So once we do this equation, okay, once we solve this equation, we'll get the roots as this one. Okay. Now we have to consider the phi n minus 1 of m. That means we will consider x to the power 2. So second degree entries are there. This is second degree. This is second degree. This is second degree. Okay. So we'll get, for second degree polynomial, we get this one. So 3m square minus 7m plus 2. Okay. So once we get this one, so this is actually 2. So this is printing mistake. This is one, not y. This is x square. Okay, I think it is. I have taken this from Grewal. So there are a lot of. You will observe the printing mistakes if you go through the Grewal book. So when the context is clear, you should not be confused. Okay, so this is 2. Okay. Now we have to find the C value. C is the phi 2 of minus of phi 2 of m. Phi 2 of m. We will write this one as it is. And the phi 3 of m, we will differentiate it. Phi 3 of m differentiate. So this is 3m square minus 4m minus 1. Now after differentiating this one, we'll substitute this value. Okay. Now here we have got the values for the values of m is this one. So C is actually we are getting as minus 3m square 7m plus 2 by 3m square minus 4m minus 1. So if m equals to 1, because from the first equation we have got m equals to 1, minus 1 and 2. So for each value we will find out C value. So m equals to 1, then C equals to minus 1. M equals to minus 1 implies C equals to minus 2. M equals to 2 implies, so from this equation if you substitute, then C will be 0. So the three asymptotes will be y equals to mx plus c. Okay. So we'll put the values of y equals to m is 1x plus minus 1. Y is minus 1x plus this is minus 2. Y is 2x plus 0. So these three are the asymptotes, inclined asymptotes. Okay, so this is how we'll find out the inclined asymptote for the functions which cannot be written as fx equals to y, or h of y can be written as h of x. Okay, so this is all regarding the asymptote. Okay, you can try both of them. The other two, the second example and third example, to find out this one and this one. These can be regarded as task to find the inclined and vertical and horizontal asymptotes. Okay, so you can take them as exercise. These two are exercises. Practice problem. So I will stop here today. If you have any doubt, you can ask me. There are around
Sir, if we take y is equals to